Yes, we can hear you.
Okay, perfect. All right. So I would like to start by thanking the organizers for inviting me to this workshop. It's really a pleasure to be able to contribute to this event. I am sorry I cannot be with you there in person due to prior commitments, but at least I can join online and I'll try to do my best. So today, I want to talk to you about a research in prostate cancer modeling. So this is work done with a bunch of collaborators from different institutions, but I want to highlight the work of Guillermo Lorenzo, who was my former student and former postdoc. But before getting into the talk itself, let's see if my slides. Yeah, I want to wish John a happy birthday. I think I have maybe a unique connection with John because although he has been one of my scientific heroes for a long time, I do think we never met in person, which is quite remarkable. I think so. Of course, we interacted through the literature by email, but I really think we never met in person. So I'm looking forward to your 65 birthday conference, and hopefully at that time I will have managed to meet you in person. But for now, happy birthday, and I hope you're enjoying your conference. All right, so before I get started, I want to give you an overview of the work that we do in my group. So we are a computational group, as you can see here at the center, and everything we do starts with a code. And we have two big areas of applications that are highly interconnected. One is multi-physics simulations, where we do work on multi-phase flows, usually phase field models of multi-phase flows, fluid structure interaction also involving multi-phase flows. And then we do work in the area of predictive medicine, including mechanobiology and cell migration. We have a big program on drug delivery of monoclonal antibodies, genetic medicines right now. And what I'll be talking about today is this topic here in the bottom right, which is prostate cancer modeling. So I have 30 minutes, and in those 30 minutes, I'd like to guide you through what I think have been 3 success stories modeling prostate cancer. The first one is trying to illustrate how modeling can help us determine when and if a patient should receive treatment. The second one, it's trying to show how modeling can help identify if a treatment has failed. But of course, it's very easy to know if a treatment has failed if you wait long enough. But the idea is you want to know that as early as possible. And finally, I want to tell you, if I have time, about the interaction between prostate cancer and another pathology of the prostate that is called benign prostatic hyperplasia. That's benign growth of the prostate. And we put forward this hypothesis that actually one disease can stop another to some extent. So just to set the stage of how I will be distributing my time, this is pretty uneven. So most of the talk is going to be on the first one, and then only if I have time, I will cover the last 2. So, okay, so let's start with story number 1, how modeling can help determine when and if a patient should receive treatment. And we're talking about cancer, so maybe you're thinking everybody should receive treatment, but that's not really the case for prostate cancer, and I will come back to this. But before, I want to tell you a little bit about the disease itself. So the prostate is a small organ in the pelvic area, which doesn't have any crucial role in the body. It has only a supporting role. Prostate cancer is a very important public health problem. The level of incidence in men is very, very high. And one interesting thing about it is that most patients show slow progression and low to intermediate risk disease, okay? And this is in stark contrast with the next bullet that you can see here, that up to 70% receive aggressive treatment and many are overtreated. So most of the cases are slow progression, low risk, but the vast majority of people receive aggressive treatment. So there's clearly strong overtreatment, but perhaps surprisingly, there is also a significant amount of undertreated people. So that points to an issue in diagnosis and treatment selection at the baseline, which we hope to address with computational models. Many people have worked on tumor growth models, but I haven't seen so many works on prostate. So let me guide you a little bit about specific things about prostate tumors. One important thing is prostate-specific antigen. This is an enzyme that is secreted by cells of the prostate. Is prostate-specific, but is not cancer-specific. That means all epithelial cells in the prostate, whether they are cancers or not, they secrete PSA, although at different rates. And it has had and still has very controversial role in the diagnosis of prostate cancer. Actually, some countries don't use it anymore as screening technology, but I will not get too much into that. Another important thing guiding decisions in prostate cancer is so-called Gleason score or Gleason grade, group grade. It comes in different names. This is a histopathological measure of the tumor aggressiveness. So basically, when the patient has a biopsy, there are some cells that are taken out of the tumor. They are looked over the microscope by a pathologist, and then the pathologist gives a score based on the pattern that they find in the cells. If they are very well organized, like if they look like uniform glands, this is not a cancer, has score 1. If they have very strange patterns, disorganized, etc., this is a score 5. And normally they give 2 scores. One is associated to the most common pattern. The second one is associated to the second most common pattern. So from that, you can guess that 3 plus 4, for example, is not the same as 4 plus 3. 4 plus 3 is worse because the number 4 shows in the most common pattern. But this is normally how this is scored. And it's very important in decision making. Another tool that is becoming more and more important is MRI. MRI resolution in the prostate is very low, but it has been improving, and now combining multiple modalities through what is called multiparametric MRI, it's a very valuable tool, okay? So the way that prostate cancer is normally diagnosed is as follows. So there is, in many places, regular screening through prostate-specific antigen, PSA, very controversial, but still most countries do it. And then this leads to early detection of organ-confined cancer, okay? So there is a regular screening with PSA. PSA is the blood test. And when this PSA goes higher than 4 nanograms per ml, usually that triggers an image, multi-parametric MRI that provides additional information. The patient undergoes biopsy. Then they look at the tumor cells under the microscope. They give a score, Gleason score, and that ends the diagnosis. Okay, and at that point, if the biopsy is positive, the patient has cancer. If it's negative, the patient is assumed not to have cancer. All right, so then there are different things that can happen. So one patient that has high PSA, has an image, biopsy comes back 4 plus 3. In most cases, they receive immediate treatment in the form of hormone therapy, radiation, or of surgery. And as I said before, the issue with this is that there is significant overtreatment, a lot of overtreatment. An alternative is so-called active surveillance. In active surveillance, patients are monitored, but they're not treated. So this is how a timeline for a patient on active surveillance would look like. There is regular screening. PSA is higher than 4 nanograms per ml. There is an MRI done. There is a biopsy. The biopsy comes back 3 plus 3. 3 plus 3 is not too bad. So then the patient is recommended to do active surveillance. No treatment at that time, just monitoring. And then there is monitoring with PSA, another image at some point. Then at some point, the PSA starts to grow again at a rate that is suspicious. As you can see here, that triggers a second MRI, that triggers a second biopsy. And at this point, it's 4 plus 3. And at this point, the patient receives treatment. So there is also a lot of people doing this active surveillance. But there's still the issues that I mentioned before: significant overtreatment and undertreatment, limited personalization, And it's also very unclear when the active surveillance should be stopped and the patient should be sent to treatment. So the idea is we want to use patient-specific computational models to aid this decision process. Okay, so the framework is based on a partial differential equation that describes the evolution of cellular density in space and time in a 3D anatomical model. We are using here the simplest model that has been used probably for tumor growth, Fisher-Kolmogorov equation. Most people, I assume, are familiar with it. This is just a diffusion reaction partial differential equation, where n is the tumor cell density. We have a rho, which is a proliferation rate. We have a mobility, d, and we have a so-called carrying capacity. So the parameters of the model are rho, d, and theta, and the unknown is n, okay? So how do we get data to fit this partial differential equation? So we can get initial conditions and the problem domain from imaging, okay? So the problem domain, which is the prostate, we obtained from the T2 series of MRI. The T2 series of MRI gives you anatomical information, and from that we segment the prostate and we get the computational domain. Then we use the so-called apparent diffusion coefficient, which emanates from the diffusion-weighted sequence of the MRI. And that is used to obtain an estimate of the initial condition for N, okay, the tumor cell density. Okay, so with that, we have a computational domain, we have initial conditions. The challenge is we're still missing the model parameters. And this has been a critical bottleneck in most tumor growth models. So let me explain why. The reason is that for most solid tumors, when they are diagnosed, very shortly thereafter, they are removed through a surgical procedure, right? So we're left with just one data point. Of course, if we only have one data point, it's very difficult, perhaps impossible, to identify the model parameters of a dynamic model. Now, the second option is that instead of surgical removal, the patient is treated with some treatment. So then we can monitor the tumor evolution over time, and that's a little better, but we still need to model the treatment response, okay? The advantage that I see for prostate cancer, in particular for patients on active surveillance, is that these patients are monitored, but they're not treated. So we can have longitudinal data at multiple time points without any treatment. So what we do here, I see this as a unique opportunity for model calibration and validation. And indeed, what we do is we take longitudinal data of one patient at 3 time points. The diagnosis time, this is time 1. Then this patient goes into active surveillance, they are not treated. Then we have data at time 2, and then we have data at a 3rd time. What we do is we use the first 2 time points to obtain the model parameters. And then we do forecast, and we compare, we use those model parameters to run the PDE forward in time. We make a prediction at time 3, and we compare with the data at that time. And with that, we validate the model, okay? So that's the idea. The computational pipeline that we follow is pretty standard. We first, from the T2 images, we segment the prostate. We also segment the central gland, which is a particular part of the prostate with specific properties. We also segment the tumor, but this time we use the diffusion-weighted series instead of the T2 series. From the diffusion-weighted series, we get the apparent diffusion coefficient using standard exponential model. Because we are going to compare images at different time points and also different imaging modalities, we need to do some registration. So for the same session, we register the ADC modality to the T2 weighted modality. And then for the different time points, we do a non-rigid registration, mapping all images to the first time point, okay? And that way we can compare apples to apples. Okay, then we generate an anatomical model of the prostate. In this case, this is based on non-uniform rational B-splines. These are functions normally used in design that we also use to do computations. And basically what we get is an anatomical model of the prostate. We map it from a torus. The prostate is topologically a torus. It has a hole. Through that hole, the urethra goes. And then we also generate an initial condition for the tumor, okay? Once we have that, as I said before, we use our data, right? And we try to find the model parameters by minimizing this objective function. The objective function is a square relative error of the tumor cell density from the image and from the model, subject to the PD, okay? So we minimize this objective function subject to the PD, and from that we get an estimate of the model parameters. This is done through standard techniques in inverse problems. We use Gauss-Newton methods. We do direct differentiation of the Jacobian, and from that we obtain the model parameters D and rho, okay? Once we have those patient-specific parameters, these are patient-specific because they are derived from data of one patient at multiple times. Then we initialize the model with the data from time 2. We run the model forward in time up to time 3, and then we assess the prediction, comparing it with the data that we also have at time T3, okay? Our computational method is based on isogeometric analysis with standard time integration algorithms. It's relatively standard techniques, so I will not go into that. I just want to show you now the results for a cohort of patients. So this is from our earlier work where we had a cohort of 7 patients. Now we have been doing the same exercise with a cohort of about 30 patients. The results are similar in quality to what I will show later. And this is how the data for a specific patient in the cohort looks like. So time 0 is the time of diagnosis. Prior to diagnosis, we have PSA data. These red dots are PSA data. You can see here PSA was 2.5, 2.6. Here it grows a little bit, but still below the alarming threshold of 4. And here it went up larger than 4, and that triggered a biopsy and an MRI. You can see here the biopsy came back with a Gleason score 3+4. This is not too bad. The patient is suitable for active surveillance. There was also an MRI done. Then the patient came back for follow-up monitoring. PSA was taken. PSA is increasing. You can see PSA went down. You may wonder why. We can go into that, but PSA is not very reliable. Anyway, then second MRI, about a year after the diagnosis. Third MRI, in this MRI, something suspicious was probably seen. And eventually, about 1.5 years after diagnosis, the patient received radiation treatment, okay? But in the meantime, we collected 3 MRIs of the same patient, and we can apply the procedure that I mentioned before. Okay, so here you can see the results for one particular patient. This is the calibration data. So this is the process that we use to feed the model parameters. And you can see here the data and the model prediction at time 2. And then with the parameters that we obtained from these, we forecasted the tumor growth at time 3. And this is the comparison between the model and the data. Now, for a separate patient, same thing, calibration. What you can see here is our anatomical model of the prostate. Here you can see the urethra, you can see the data, you can see the model prediction. These are just cross sections. And the color scale that you see here is N normalized by the carrying capacity. So red means the tumor is there, blue means healthy tissue. And then again, this is the calibration step. And at the forecasting step, this is the comparison between the data and the model, okay? So now, if we collect the data for all patients in our cohort, which, as I said, were only 7, but you can, we now have results for 30 patients. They look pretty much like this. this is the prediction, model prediction for tumor volume here. And this is the data for tumor volume. So you want all of the data points to be on the diagonal here. That would mean perfect agreement. And you can see they are not too far. The agreement is pretty good. And this occurs both in the fitting scenario. So here, obviously, the fitting is going to be better than the forecasting. The fitting is we're just trying to fit ×1 and ×2 and ×2 to the model to find the parameters. And in the forecasting, we don't allow the model to see the data at ×3. We just forecast what's going to happen at ×3. But still, actually, we show there is no statistical difference between the accuracy of the fitting and the forecasting, which is pretty good. And we also compare these in terms of the dice similarity coefficient and the root mean square error, and it's reasonably good. Okay, so this was recently published in the Cancer Research Communications. It was selected as editor's pick actually recently. The other thing that we did is once we have this model, we try to define model-based risk classifiers. So we look at our model, we look at our model parameters, we look at quantities that can be derived from our models, and we want to understand if those quantities identify or can separate high risk versus low risk patients. Okay, and we came up with two classifiers. The one here is the mean proliferation activity. This is the proliferation term in the equation. It's integrated over the tumor. When you do that, you get a single number, PM. And then we also define this tumor index, which is the volume of the tumor over the volume of the prostate multiplied with the average cellular density in the tumor. Okay. And what we observe is that these two parameters combine, PM and NT. If you look here, you can see that in our ROC curve, they do a decent job telling the difference between lower Gleason score and higher Gleason score. So this would be low risk and this would be high risk. Okay. Actually, NT by itself cannot really separate low risk versus high risk, but PM by itself can separate low risk and high risk. They are significantly different, as you can see here. And when you use both together, you get a slightly better result, and you get this ROC curve. So again, we're exploring this in a much larger cohort right now, and results are encouraging. Okay, so now I want to tell you a little bit about how we plan to extend this in the future. So in this problem, there is obviously a lot of uncertainty. There is uncertainty in the images, there is uncertainty in segmentations, and there is a lot of work to treat those types of uncertainty. But I was talking to my colleague Ilias Bilionis here at Purdue, and what he said, he's the expert on our uncertainty quantification. I'm not, but he said one of the biggest uncertainties that you have, which I totally agree with, is model form uncertainty. In other words, is your model, is your PDE correct? Okay, and this is obviously a question that I never stop asking myself, right? So he has the right tool to be able to identify how much of the uncertainty in our results comes from uncertainty in the PDE, or uncertainty in segmentation, or uncertainty in any other aspect of the pipeline that I described. So he came up with this theme, which he called physics-informed information field theory. And basically, this is Bayesian statistics over fields. Okay, so it's a probability measure in a functional space. So when you think about a probability density function, normally here in the horizontal axis, you will have a number, right? And then if you are thinking about the height of a person, right, then this is a number. This is, for example, 1.75 meters. and then you get a probability for that. But here, in this case, this is a probability measure in the function space. So every point here on the horizontal axis, this is a function itself, right? It's a function, not a single number. So samples of this thing, this probability distribution are functions. And then the mathematical framework that he had to use for this is the framework, it's the same framework that is used in quantum field theory, okay? So it's pretty complicated. Actually, one of the things that you have to imagine, you have to take the expectation of this thing, right? So then you have to do an integral over all possible functions in a functional space of your choice. So that's pretty difficult integral to do. And actually, there are mathematical problems with it in some cases. But then the idea that that he proposed is the following. So we can have a physics-informed functional prior. Okay, that would be the probability distribution before I see any data. And that would be something that looks like this. So it has here a parameter beta that is a metric of our confidence in the model. And then this is if you have an energy in your problem, this is an energy. And if you don't have an energy, it would be the residual of your PDE squared, right? So this tells you how confident you are in your PDE, right? So your prior is a solution to the PDE in a way, right? So if this function looks like this, like it has a very strong peak, then you have a lot of confidence in your model. And then if it becomes flatter, then you don't have a lot of confidence in your model, right? And here the average or the mean, it's the solution to your PDE, right? And then this is your prior, but then you provide data and you get a posterior, right? And when you get the posterior, you can evaluate, or Elias can evaluate how much uncertainty you have in each of the process in your pipeline. So, okay, so this is what we plan to do in the future. I think I will, I see something in the chat, hopefully. Okay, 1 minute. Okay, so 1 minute. So, okay, let me go to this story, number 3, very quickly. So interaction of prostate cancer and BPH, benign prostatic hyperplasia. So as I said, BPH is abnormal but benign enlargement of the prostate, okay? And the interaction between BPH and prostate cancer, they're poorly understood, right? However, on the other hand, we also know that compressive stresses slow down tumor growth in vitro. This has been known for a long time. And here, there was a lot of data in the medical literature showing that larger prostates have a tendency to harbor less aggressive tumors, okay? So no matter how you look at it, this is the log of odds, and this is the prostate volume. As the prostate volume grows, risk of aggressive cancer at surgery goes down, aggressive cancer at biopsy goes down, extracapsular extension, which is tumor going beyond the prostate, it goes down too. And there was no clarity in the medical community what the reason was. So what we propose is that when we have benign prostatic hyperplasia, because the prostate is growing and it's a very confined organ, has nowhere to go, as it grows, it generates a lot of compressive stress, and that slows down tumor growth, okay? And then following up our work, which was from 2019, there was people imaging the prostate and really showing that there is huge compression in the peripheral zone of the prostate where most tumors are located. So there's like encouraging follow-up from the medical literature. Okay, with this, I'd like to finish. We're hiring students and postdocs for a project on delivery of genetic medicines. I'd like to thank all of you, and I would be very happy to take any questions.
Thank you. Any questions?